In this lesson, we're going to go over sigma notation. We're going to look at these two examples pretty in depth. Later, we're going to make sense of a lot of different formulas, and we'll take a look at some properties of sigma. So let's take a look at how we actually read these things written in sigma notation. So this big symbol here is the Greek letter sigma, and in math, the symbol means to just add things up. So let's just ignore this for a second and take a look at what we have here. This is actually just a geometric series. We're used to writing something like n minus 1 in the exponent, but it doesn't really matter. We're starting with 3, and we're going to multiply it by 1/2 over and over again. That's represented by this exponent I. So it's kind of a bummer that they use the letter I. It's not the imaginary number I, but they used I for the word index. And if you're indexing things, it just means that you're counting them up. So it's really just the same thing as the term number. So underneath sigma here, we have something called the lower limit. It says I equals 1. That just means that our first term, we're starting with the term number 1. And you could contrast that with over here, we have I equals 0. That means that our first term is going to be the 0 term. On top of the sigma, we have the upper limit. The first one is infinity, the second one is 24. So we have lower limits and upper limits, and that just means that we're going to start by plugging in 1 as our first term, and then we'd plug in 2, and then 3, and we'd go all the way up to infinity. So we'd keep plugging numbers in infinitely. And that means that this whole thing is an infinite sum. The one on the right starts at 0, so you'd plug in 0 for the first term, and then 1, and then 2, and you'd keep plugging things in and writing the terms out until you get to the 24. But this one stops at 24, so we would call this one a finite sum. So like I said before, this first thing is a geometric rule, and this one is actually an arithmetic rule. And if you think about plugging 0 in first, that means that our first term, this would just cancel out, and we'd start with -5. That's kind of like your y-intercept. And then it's kind of like you have a slope of 2, so you'd be increasing by 2 every time. So adding 2 means it's arithmetic. So remember, in a geometric rule, the thing that you're multiplying by over and over again, that's the common ratio. And in an arithmetic rule, the thing that you're adding every time, that's the common difference. So now we have some basic vocabulary under our belts. Let's take a look at actually working with these. Let's try writing out the first 5 terms in each series. So for the first one, remember, this is an infinite series. It's going to go to infinity, but we're just going to write the first 5 terms. And we're talking about a series, which means that we're adding things up. So when we separate the terms in the series, we're going to put plus signs in the middle, not commas. So the lower limit here was 1. That means I'm going to start this series out by plugging 1 in for I. For the second term, I'm going to plug in 2 for the I value. Remember, I want to separate these with a plus sign. So for the third term, I'm going to plug in 3 for the I value. To get the fourth term, I'll plug in 4 for the I value, so 1/2 to the 4th power. The next term would just be 3 over 32. So here's this infinite sum, and we just wrote the first 5 terms of it out as a series. Let's do the same thing for this series, except for this one starts at 0. So if I plugged 0 in, 2 times 0 is 0, minus 5 is -5. The next term is when I equals 1, so if I plugged in 1, 2 times 1 is 2, minus 5 is -3, so plus -3. You don't really have to write the plus here, you could just write -3, but I'm just showing you that this is a series, so we're separating each of these by addition. So the next terms, let's see, I plugged in 0, I plugged in 1, so now I have to plug in 2 for the I value. If I plugged in 3, so that would be plus 1. If I plugged in 4 for I, this would be plus 3. Again, this series goes all the way up until 24, but we just wrote the first 5 terms of it out this way. Something else you could be asked is to find the 5th partial sum for each series. Partial sum just is telling us that we're not finding the entire sum. For instance, this one goes up to infinity, so that might be a lot of work to add all those numbers up. This one goes to 24, so we're not adding all of them up. Just the 5th partial sum just means add the first 5 terms. And we just wrote out the first 5 terms, so let's just add them up. So here's our first series again written out. If I wanted to add all these fractions, I would need to get common denominators, and they're all powers of 2. So if I multiply all these numbers in order to get up to 32, that should work out pretty nice. So I'll multiply the first fraction by 16 over 16, the second fraction by 8 over 8, the third fraction by 4 over 4, and then this last one by 2 over 2. So if you add all those up, you'll get 93 over 32, and that's our 5th partial sum. That's what the first 5 terms added up equal. So here's our second series written out. And actually this is pretty easy to add up because -3 and +3 cancel, -1 and +1 cancel, and we're just left with -5. So there's our 5th partial sum. So that didn't take too much work, but it did take us some time just to add up the first 5 terms in these series. If I wanted to know the 100th partial sum, that would take quite a while. And even if I used a calculator, I don't want to sit here plugging all this into a calculator to add up 100 terms. But since all these sequences follow such nice patterns, there's actually a lot of nice formulas we can use to speed up the process. Now this looks like a lot of information here, but we already know some of this. This first equation, that was the explicit rule for an arithmetic sequence. And this one is an explicit rule for the geometric sequence. Then we have a few formulas that start with the letter S. S is for sum, but this last one shouldn't have an n there, so just scribble that out. There's no n in this formula here, which makes sense because in this first formula there is an n. We're counting the term numbers. What this formula does, it helps us add up arithmetic sequences. So you can think of S for sum or series, and n is the term number. Since we're adding up an arithmetic series, we do have to stop somewhere. If you go on forever, you'd just be adding up numbers forever and it wouldn't equal anything. It would just be like infinity. But we can evaluate the sum if you have a certain number of terms, a finite number of terms. So we do have to know the first term value and then the nth term or the last term value. But plugging things into this formula will help you find the sum of any number of terms in an arithmetic series really fast. This formula does basically the same thing. So S is for sum. There's an n here because this is a finite series. We have sigma notation now showing us that we're going to start with a lower limit of 1 and we're going to go all the way up to n. So there's a lot of variables floating around here, but n is just the term number. So all this stuff means is just that we're going to start with the first term and we're going to keep adding them up until we get to the last term. And what is the stuff that we're going to add up? It's this stuff here. So this is some first term and then this is r to some exponent. So this is just a geometric series. So this is the sum of a finite geometric series. And I have to specify that this is finite and you'll see why in a second. But here's the formula all the way at the end. This is what you actually use. So this is a big long string of stuff here, but they write it this way to show you that S is for sum. We're adding up a geometric series, and this is what you actually do. So to use this formula, you just need to know the first term, the common ratio, and then the final term number. And if you need to know the final term number, remember you can get that from the upper limit on the sigma. The formula on the bottom kind of starts the same as this one, so it's for another geometric series, but this one goes to infinity. So it seems kind of strange, but with geometric series, if the r value is less than 1, or actually if the absolute value of the r value is less than 1, so that means that r could be like negative 0.3, the absolute value of that would still be less than 1, that's okay. So if you have these small kind of r values, you can add all the numbers up in an infinitely long geometric series, and it will give you just one specific value. And you can find that value by using this formula. All you do is you take the first term and you divide it by 1 minus the common ratio. So if you were given some big infinite geometric series like this in sigma notation, you were told to add it all up, you just use this simple formula. And all the values you need are right here in the sigma notation, the a sub 1 and the r. This last column just has a couple like special case type formulas. So over the years, people who have nothing better to do with their lives than to just sit around and add numbers up and look for patterns have found these formulas. So let's take a look at this first one. It just says sigma of I, and I starts at 1 and it goes up to some ending value. So I is just going to be a bunch of whole numbers. If I wanted to add up a bunch of whole numbers, I would use this formula. And I guess I was saying whole numbers, but it does work with integers too. So like if I down here started at negative 5 and it ended at 10, you'd be finding the sum of all the numbers from negative 5 to 10. Now we do have to say consecutive because if I is starting at 1 and then it's going up to this number up here, you're counting up by consecutive numbers. So you'd be plugging in like 1 and then 2 and then 3 and then 4 and then 5. So if you want to add up all those numbers in a row, you can just use this formula. So all you do is you take your last term number, multiply it by 1 more than that last term number, and then divide by 2. What's really interesting is you can actually show that this formula and this formula are the same thing in a certain case. That might be kind of interesting to look at. But for right now, let's just take a look at the next formula. This one starts with I squared though. So if I wanted to add up a bunch of perfect squares, I would use this formula. And the last one is if I want to add up a bunch of perfect cubes. So all of these I would consider formulas, like they're things that help us speed up a process. The next four are what I'd consider properties of sigma. This first one says sigma of c, and c is just some constant, so some number. So if I was adding up the same number over and over, let's just look at an example, like add up a bunch of 4s from I equals 1 to some number n, let's just say like 5. So this means that I'm going to take the number 4 and I'm going to keep adding it to itself this many times from 1 to 5. So that would look like this. And that's just 5 4s. So 5 times 4. And that's what they're showing you here. Just take the constant that you're adding here and multiply it by the top number, the upper limit. The next one says sigma of c times a sub I. And I is some index. It's going to go like 1, 2, 3, 4. So this would be saying like c times a sub 1, and then c times a sub 2, c times a sub 3. So we'd have a series like this. We're just adding up all these terms, and it could go on forever. It could go up to some value n. But if you look at this property, what it's telling us is that we can take the c value inside the sigma and just bring it out front and write it there. But that makes sense because if you look at this here, each of these terms has a c in it. So we could factor a c out, and we'd be left with a sub 1 plus a sub 2 plus a sub 3 plus, and that would go on forever, or up to some n value. But that's just the sum of all of the a terms, like this, like a sub 1, a sub 2, a sub 3. That's just the sum of all of those a terms multiplied by c in front. So I summarized that here. I said you can factor constants out of sums. That's why this property works. This next one says a sub I plus b sub I, and it's telling us that we can break this sigma notation up into two sigma terms. So imagine plugging in all of these different I values. So you'd have like a1 and b1, and then you'd have a2 and b2, and then you'd have a3 and b3, and we're adding all these up, and these are all being added inside here too. But if you add things up, it doesn't matter what order you add things. So maybe we could rearrange this so that we take all of the a's together and all of the b's together. But now if you think about it, this is just adding up a bunch of a terms. That's what this says. And this is adding up a bunch of b terms. That's what this says. If you remember way back to probably like elementary or middle school, you probably learned about the associative property of addition. That's what this is showing you. And finally, the last one is the same thing, just with subtraction. So all of these formulas and properties got pretty abstract. Let's just write out one example and use some of them. And I'm actually going to go with one of the examples that we started the lesson with. And remember, 2i minus 5 was arithmetic. So if we look back at these formulas we learned, I could find the sum of an arithmetic series with this formula. So to do this, I would need to know the number of terms, which in this example was 24. I'd also need to know the first term value and the last term value. So I'm just going to write all this information over here, and then we can plug some stuff in. So n was 24, that's the number of terms from 1 to 24. But then a sub 1, that's what you get when you plug 1 in to get the first term. So if I plugged in 1, that would be 2 times 1 minus 5. 2 times 1 is 2, minus 5 is negative 3. And then to get the 24th term, I just plug 24 in. So 2 times 24 minus 5. So that would be 48 minus 5, which would be 43. Now we just have to follow that formula, which said s sub n, or in this case s sub 24, the sum of the first 24 terms, is 24 over 2, that was n over 2, and then take the first term value, which was negative 3, and add the last term value, which is 43. All right, so negative 3 plus 43 is 40. Now I just have to multiply that by 24 over 2, but actually 24 over 2 is 12. And 12 times 40 would be 480. So using this little formula helped me add the first 24 terms of the series up really fast without having to evaluate every single term number. But check this out, we can start this process over and use some different formulas and get the same result. This time I'm going to use the sigma properties, so these help me break up more complex sigma problems. So this one says 2i minus 5. Basically there's two terms in there, so I'm going to break those up. This last sigma property shows me that I can just take these two terms and write them as two different sigma terms. So here it is broken up. It's the same sigma stuff in front of each term, but I'm subtracting them in the middle, and then the first one I have 2i and the second one is 5. And I can take this one step farther even, because here I have 2 times I. And this example was showing you that if you have some constant, like in our case 2, times some term numbers, you can just factor that 2 out. So now it looks like this. This one can be evaluated using one of the sigma properties. Remember, if you're just adding up this same constant 5 a bunch of times, in this case I'm adding it up 24 times. So this second term here, I could evaluate that as just 24 times 5. And whatever that is, I'm going to be subtracting that value. So 24 times 5 is 120. So I know at the end of this problem I'm going to have to subtract 120. So I'll come back to this later. Over here I'm adding up I from 1 to 24, and we have a formula for that. That was this one. So to use this formula, you just have to know the number of terms you're looking at. In our case, is 24. So I'm going to take 24 times 1 more than that, so 25, and then over 2. So 24 times 25 over 2. And whatever that is, that's the value of this sigma here, but I'm still multiplying by 2 in front, so actually I'm going to do this. And then the 2's cancel, so I'm just left with 24 times 25, which is pretty big. That actually gives you 600. So if you take 600 and subtract 120, you get 480, and that's the same value we got before.